So yes, hello everybody to the last session. I hope you're still with us. And let's see, oops, what we can do. First thing, I had to change the title of the presentation. I submitted it about a year ago, and it's now, when I was actually making it, I figured out I had to start at a single core and not two CPUs so that everybody can follow the whole process. But it's the same session from a content. I just choose to change the title to Beyond One Core. Quickly, and I'm pretty sure in the virtual world, this is not going to go well with all the animations. But so a little bit about me. That's my name, Thomas Grohser. Same as Klaus, I'm from Vienna, Austria. One difference, I live for the last 8 years in the United States. I work here. I'm with SQL Server almost till the beginning of time. So I started using it in 1994, so 10 years after Wonder Woman. And yeah, I'm busy around, and you can read this on the shared slides if you're interested. So before we start the whole thing about how to look at how to make machines big and responsive, the thing I had to learn over the years is how to compare stuff, because hardware vendors are really nice in disguising what they're actually selling. Yeah? And so the good saying in the English language, comparing apples and oranges, is not always as easy as in this case. Yeah? In many cases, I have to deal with stuff like that looks more like this. Or sometimes it's even harder because one disguises inside the other one. And then there's the last and biggest problem I have. If you have a clear apple and a clear orange, and then you give it, it gets like masqueraded behind some obstructions, and that's what I call marketing. So marketing puts a big wrench into it. It's the problem is the louder a company pushes a feature, the more I learn to get suspicious that this might not be the thing that actually helps me. Yeah? And these pictures were not inspired at all by this person. So during the whole presentation, I will always tie it back to 4 workloads I use to explain this. Yeah. One is a machine that should have the goal of have the lowest latency, meaning each individual query should come back as fast as possible, yeah, as thing is. And it might be that this is the case. I often see this where there's only one connection to the SQL Server and there's only one query at a time. Yeah. And everybody's complaining that everything is so slow because, yeah, it's one. And everything is happening once after the other. So low latency machines, if I send a query, I want the answer as quickly as possible. The second one is high concurrency OLTP, meaning I want lots of the first one at the same time. Yeah? I want to have 1,000 people that can click on buy this on our website at the same time. I want to be able to run 500 stockbrokers and deal with each one at the same time, stuff like this. Small queries, lots of concurrent connections, nothing big, everything's quick and small queries, but I want to run thousands of them in parallel. Third kind of category I'm going to talk about is high throughput, basically the data warehouse. I have a large database. I want to read as much data from it as I can at the same time. Usually there's only a few connections at the same time, and they all hammer the machine with scanning through large amounts of data. And the last one is the generic server and the server that you use for virtualization. They are pretty much the same. They're interchangeable from a hardware perspective and point of view. It's the garden variety machine that everybody should use or is using. That's the thing that you want to do. And everything I'm going through, every technique I'm showing during this talk, I will then tell you if it's for which one of these 4 categories this makes sense and for which one it doesn't. Yeah. So before we go through that, we have to work through a little bit of theory, how scaling and parallel workloads works. What can you do to make things go faster? Yeah? And for everybody to understand that, if you attended the previous sessions today, this is picking up where Klaus just left off. Yeah. So we already optimized all our table structures, everything. We optimized the query processor, came up with a perfect plan. We already tuned everything so that we don't have any ledges and don't have to wait for acquiring ledges anymore. Yeah, we still need the thing to go faster. This is what this talk aims about. Yeah, so we have to talk. What tools do we have in our toolbox? What we even do? We can optimize stuff. Again, we talked about it. We can reduce stuff, which is funny, and not many people actually do that. The best way to speed things up is do less work. Scale up and scale out. Yeah? Optimize is basically get the same amount of work done by doing it more efficient or faster. So you're buying a CPU with higher clock speed, or you're tuning your queries, basically. Reduce is do less work. Find all the useless code in your database that runs for no reason. Yeah, I don't know how many times I saw queries doing the same thing 5 times over, just to at the end have the results combined instead of doing it in one step. Stuff like this. Yeah, and then scale up is goes, hey, take one server, make it bigger, and scale out is buy more servers and find a way to transfer workload across multiple servers. So optimize. You're basically having a certain amount of workload and you run it. Oops. You have your workload and you run it piece by piece. Yeah? And if you can run it faster, you will save some time. Yeah? So that's the concept of optimize, and very simple. And trust me, we need to understand this to later on understand what CPUs are doing. Yeah? The second one is reduce. We get rid of a bunch of stuff that we don't need, which again gets the whole thing done faster. Third one, scale up, is instead of doing it one after the other, we're doing it all at the same time. Yeah, great. Problem with that is this is a very rosy and awesomely optimistic approach, because that assumes that these n workloads that we're running in parallel do not depend on each other. It's much more likely that it's going to look like this. This is, on the other hand, the opposite, the worst case scenario, where each and every workload depends partially on the other. There's one worse one. If each and every workload fully depends on the other one, yeah, then it would take the exact same amount of time. But even if it's partially overlapping, thing is, we're still saving some time, but not as much as in the previous case, which is the ideal. So with that, thing is, scale out is basically the same as scale up, with 2 additional steps, 3 additional steps in there. You have to send the workload out to the different nodes. You get the result back. You have to collect the results, and then you have to combine them. So scaling out overall takes longer, but therefore you're not constrained by the size of your server, what you can put in. And depending on what you're doing, it might be a cheaper approach than scaling up, which over the last 5 to 10 years, I found is no longer the case. When I started doing this about 20 years ago, every time you doubled the size of your server, you basically had a 10x cost increase. That's no longer the case. These days, when you double your server, it's about twice as expensive. And therefore, a lot of things have shifted. So, much more clever people than me came up with a formula that describes what I just explained. It's basically how much parallelism can I get? And I have to plug that in twice. And how many parallel threads can I run? That's this one. And that. So that formula says nothing, but if we visualize it, it makes suddenly total sense. So what does this diagram shows us? At the bottom, and on the x-axis, we see how many cores we have. We have 1 core, we get exactly 1x of performance. That's that little point here. If we have 2, we probably get 2, 4, 8, 16, and then 4096. And what these different colored graphs are is the p-value varies between what I plotted out was 80% to 99%. Yeah. So what this shows is at some point we have diminishing point of return. Yeah. So between here and here, we get like 10, instead of 40 times as fast, we get to 50 times, but we have to do 8 times as much CPU. So we're going from 256 cores to 4096. That makes no sense whatsoever. Yeah? If I can get my workload to be 99% independent from each other, I am getting much longer a reasonable return on my investment. Yeah? If I'm crappy and I don't pay any attention, I'm basically flat out anywhere above 4, 8 cores. Yeah? Yeah? So where does this point us with SQL Server? Yeah? This is what I've experienced over time in the real world out there. Yeah? Well-tuned queries, not constrained by locking and blocking. And things. The red curve is you take SQL Server out of the box, you click next, 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 and you run your stuff there. Yeah. The blue one is you tweak a couple of things when you install it, and the black one is you put a lot of effort into configuring the system and designing. So basically, this is today's session. This is we don't do anything, and you can see this can give you more than a 2x versus I'll just put in the box. Yeah? If you put buy crappy hardware, you're down here, yeah, and you will never go up. Yeah, that is a point that it stays. You might not notice because locking and blocking might keep you down there anyway, which is a different problem for someone else to explain how to solve that. So, how to get from 1 to 32 CPUs without completely messing it up. Yeah. So long time ago, in a server far, far away, we had CPUs with 1 core, and these were the good times because it was almost impossible to mess up hardware because it worked all the same. Yeah. So I had that 1 core. Whenever that core decided I need to access memory, I can do it. Whenever I have to do IOs, I can do it. I am the happy king. I run 1 thread. The thing is, occasionally I switch to another work, but that's it. Yeah? There were nothing that would stop that core from running. And at this time, the only thing that Intel and AMD at the time were fighting about who has more gigahertz, or back then basically more megahertz on clock speed. Yeah? Then the problem started. Yeah, not the problem. So at some point, even back then, when we just had 1 core, the actual limitation for a database server would have been memory. Yeah, because memory is always slower than the clock speed inside a CPU. Yeah, you can run data between CPU registers much, much faster than you can ever exchange it with memory. Yeah, and we will come to timings later on, but on modern machines, to access memory, it takes about 19 clock cycles. So if all you do is shuffle memory from one place to another, every 38 cycles, you get 1 unit of memory transferred. Yeah? And 1 unit, I'm keeping it vague right now because it really depends on how the system is configured, what that unit is. But worst case scenario, it's 1 byte. But hopefully more. But 38 cycles for moving just data from one portion of memory to another one, which is probably something that a page split would do or something like this. This sounds very, very slow to me. So memory is a problem. For that reason, one thing that the CPU world did is they invented caches. Multiple levels, L1, L2, L3. In the early days, there were even ideas about an L4 cache, which was outside the CPU, it was a faster memory chip. Things might come back or not. And what they added was direct memory access between the I/O devices and the memory. Yeah? Still, we were at times where we still had one core, but they started implementing caches because the memory was the bottleneck, and that gave CPUs a massive performance boost. Moving on, we had a second core, and now it gets interesting. The moment we had a second core, all developers had to relearn how to write code, because unless you're running multi-threaded, you're not gaining any performance from two cores, because your code would still just run on one of them. Problem is, once you started using multi-threading, you had to do all the synchronization. We are back to the previous session with ledgers, locks, stuff like this to handle this. But even on a lower level, the CPU has to make. Yeah? Just assume this CPU will run some command that pulls some data and has it in its L1 cache. Now, that core runs another command that wants to access the same memory. If we would just pull it again from RAM and put it in the L1 cache, it would still have the old value. Yeah? So even down on the CPU level, the CPUs must have something internal that is like the ledge we talked before to make sure that these caches don't hide the data from each other. Yeah. So what would happen is when this core requests the data, that L1 cache would basically ask the other caches, hey, any one of you having that data already? If yes, they would transfer it from there and not from the memory. If in some systems, they would write it back to memory and pull it in again. Yeah, stuff like this. So having multiple cores adds another thing is, yeah. And believe it or not, that costs time. Not much, but it costs. So if you look at a modern CPU, we not just having two cores, we have things like 8 cores here, which are in the middle. Then they have the PCI Express interface and multiple memory controllers so that memory can run much, much faster by accessing it in parallel. So if you read a couple of megabytes, it would, the memory controller and the OS would make sure that the data is nicely striped across these memory modules. Yeah. The QPI links are how CPUs are connected to each other. I'm not talking anymore about CPUs that are connected through buses, because that's not the case anymore. That 10 years ago, 15 years ago, that was the case. It's no longer the case. I completely removed all that from all my memory and teachings. High core CPU looks exactly the same, just more of these little cores here in the middle. Yeah. I deliberately choose an Intel CPU here because the next slide will show an AMD CPU in comparison. So what this shows is 28 cores with the same interface. This already shows you that when we go back to this one, that a CPU with more cores will have more overhead because the sharing is between much more cores and the synchronization happens more. Yeah? So how can we use a single CPU for? There's two things. If you want the lowest latency machines, that's where you use a single CPU for. No other, if you have more than one CPU socket, you are compromising on latency. And I will explain this in the slides coming right after this. Yeah. And the other one I recommend single core CPUs for, single sockets machines for, is generic and virtualization. It's, if you have the choice of buying a server with one CPU and 20 cores, or a server with two CPUs, 10 cores each, if you don't want to deal with hardware and balancing and configuration and anything else, if you just want it in the data center, you are better off with a machine that has only one CPU, because you will run into less, you will have the gained latency will make up for other shortcomings. Yeah. You still have enough IO, you still have enough of all the other stuffs. Can you push a 2-socket machine to more work? Yes. But again, you need to do something. If you don't, just go with one CPU socket. Okay, any questions so far? Nope, moving on. Hyperthreading. We have to talk about it because it doesn't go away. So what's hyperthreading? Without hyperthreading, you have inside the CPU, you have your registers, your flags, everything, and then you have all the little transistors that do your math, multiplications, adding stuff, shifting things around, comparing things, everything. And the thread that runs on that core can access each one of these functions at any point in time they want. If you have hyperthreading, you have two of that state machines, and they share the tools basically. So here in your garage number one, you have one mechanic that has one set of tools, and whenever he wants to repair your car, he just picks a tool and does it. With hyperthreading on, you have two mechanics that have to share the tools. Yeah. Can one mechanic diagnose your one engine in one car while the other one is messing around on it? Yes, and that's what makes it faster. But if both mechanics need to use the same tool at the same time, one has to wait. And this gives us, from a single thread perspective, you actually get 30 to 40% less performance when you turn on hyperthreading. So this guy here runs on 30 to 40% slower than this guy. If you look at the whole core that has two of these hyperthreads, you gain 20 to 40. So if you take these two together, you have plus 20 to 40%. Yeah, and the 20 to 40% really depends on what kind of code you're running. Yeah, and this is mostly what I see with SQL Server. Yeah, so from a single thread, you're slower, but overall you're faster. So how do we translate that into our 4 sets of standard workloads? Low latency, no. High concurrency, no. High throughput, yes, turn it on, because high throughput means I'm doing a lot of things in parallel. I'm doing a lot of things here. Gaining these 20 to 40% gains me 20 to 40%. Yeah. And you should also turn it on your generic servers, because most likely you have more like high throughput work than low latency. Questions? Good. So what happens if we add a second CPU? The picture just got way more complex. Before, we just had to deal with concurrency between two of these cores. Now we have to deal with concurrency across CPUs. If this guy needs to, let's get rid of this. If this guy needs data that is in this cache here, it has to go to get it. Yeah. Again, it could be, depending on the CPU design, that they go exchange it directly between the level 3 caches, but it now has to go a long path, yeah, to the other CPU. So every time you access memory in a machine that has more than one CPU in it, and I'm not talking cores, I'm talking actual CPUs, you will see this. You will get from 76 nanoseconds on a modern machine with average memory thing is, and this goes up and down depending which memory modules you use, which CPU exactly you're using, how you configure the machine. It even depends on how you cool your data center. Yeah, but basically you're going from 76. So if this guy needs to go here, but now it needs to go here, you're going from 76 to 98. If it actually is cross CPU, you are at 139 nanoseconds, which is almost twice as long as before. So you just cut, by adding a second CPU, you cut your memory performance basically in half. Again, in the real world, it's not that. And if you remember earlier this day in the very first session, when we were talking about Pneuma nodes, that's why SQL Server was one of the very first applications in the Windows field embracing Pneuma. Because if SQL Server can keep the memory of threads that run here, it's going to run and not have to go to the other CPU. They save a lot of time. Let me clean this up a little bit so people understand. Yeah. So this is the big thing when Pneuma helps you. Pneuma gets you from here to here. Yeah. which is not as bad of an increase as when you go from here to here. So what happens is, and this is where marketing comes in, if you look, there's 28 core CPUs and there's 56 core CPUs. This is how a 56 core, if you add 2 of these CPUs, this is how it looks like. These QPI things are now no longer dotted because they are actually connecting the things. And whenever we are exchanging data, this is going through these QPI links. Yeah, and yes, everything is self. You have twice as much I/O, you have twice as much memory, but you have the delay if the memory has to go through the QPI bus. There's a throughput limit. This thing is like 3 units wide. Here we have 12 units, so it's a big difference. So then, whereas more marketing kicks in. Intel built a CPU that has 56 cores. No, it did not. It just took 2 CPUs and put them in one box. Yeah, the 56 core CPUs from Intel are actually 228 core CPUs that are connected. AMD does the same. AMD's 64 core machine is great, but it's actually 8 core CPUs that sit within the same chip. And if this guy needs to get to memory from here, it has to, and then if it's in this guy's cache, this guy has to do the nasty through there. They cannot just cross access. So this 64 core thing is very different than a 28 core Intel CPU from a memory access perspective. They're still all good CPUs, don't get me wrong, and they all have their use cases. When you're optimizing for them, you have to be aware where the limits are. So as long as you run a max stop that's within 8 on this CPU, and it can run within here, and then takes out a memory portion that it only runs here, it's perfect. If you increase that to 12 and you have add this, you suddenly decreased your performance massively on that CPU. So this is what you have to think about. Well, it's even funnier when you take these Intel CPUs that are actually 2 in one box. You can actually combine 2 of them, but then what you're actually getting is a design for a 4 CPU machine, which we will talk in detail before. But since theoretically, based on marketing, you're combining 2 CPUs here, but under the hood, you're actually combining. The reason I'm bringing this up is when they had the CPU before, we had these 3 links between the 2 cores, between the 2 dies. Yeah. Now, if you combine it with another CPU, this is down to 1. So whenever this guy needs memory from this die over here, this has now to squeeze through that 1 connection. Yeah? And that furthermore slows it down. So just choosing which one of the CPUs you're using makes a massive difference in when it comes to accessing memory. And trust me on one thing, databases is nothing else than reading and writing memory all day long. The calculations that are done inside a CPU are minimal compared to the amount that needs to go in and out of memory and in and out of storage. Yeah, databases are not computation high applications. Even if you do some math in your query like thing, yeah, that's nothing compared to the work that it takes to shuffle around the data. So use cases for dual CPU, it's definitely no more low latency. It's not for high concurrency. The dual CPU machine is another good choice for a generic server. If you want less work, you go with the 1 CPU. If you want to do a little bit of configuration work, you go with the 2 CPU box. Just fine. Same for virtualization. Just try to stick on one of the 2 CPUs that is in the box and you're fine.
Okay, so we've got a handful of questions that have stacked up here in the last few minutes. So we'll kind of work our way through these. So this one is from about 7 minutes ago, so maybe 4 or 5 slides back. So do we know if the hyper-threading instruction sharing works the same way on AMD's simultaneous multi-threading?
Yes.
Okay. All right, so there's that. And then we've got a handful more here. So from anonymous attendee, So a 4 CPU, 24 core this hyper-threaded is not an optimal setup. And then in parentheses it says 2.2 gigahertz, which I'm assuming is clock speed there.
Yes, can be. And again, there's use cases for it and there's not. We will talk about the 4 CPUs coming soon. We're only up to 2, so that's a 4 CPU question. But the indirect preview of me showing this one where you have a fake 4 core, fake 4 socket machine, yes, that's bad. That's not good. Yes.
Okay. And then we've got, looks like somebody just picked up one in Slack, which is awesome to see. So we have, I would say 1.5 more. So we'll do this one next and we'll see what you think about the last. It's fairly broad. So this says, are there any tools available that could be used to measure these timings over time? For example, yes. I believe Core Info. Okay, go ahead.
So the one I use it's called Busy. And it's on a website that's called SQL Stress.com or .org. I will add the link somehow to the download thingy. Yeah, it's a very simple tool, but it gives you thing is you basically start it and tell it how much memory and how many times in parallel you want to move it between cores, and it does it. So if you say 2 cores. So 2 locations and 1 gigabyte, it moves 1 gigabyte, it allocates a gigabyte on one CPU and 1 gigabyte on the other one, and then copies it from one side to the other the fastest possible way that CPU can do it. And if you do the same and you give it do this for 64 cores at the same time, it will do the same on 64 cores. And the reason you have to specify the size, if you, for example, put the size in something that's within your cache size, you will see big difference. So you have to understand the tool was not designed for that, but it's you can awesomely measure that stuff. Yeah? Because there are very few tools that measure memory performance correctly. You still have to do 10, 15 runs and then average out the values to get consistent readings, because trust me, moving your mouse can affect the readings. Yeah. It's not like an awesome tool with a GUI that has you click and it tells you everything. But yes, there are tools.
Okay, cool. So we just got another one in. Then I'll give you both of these. I suspect you're going to want to hold the last one till the end. So the broad one is, how do we determine the best hardware configuration? So if you want to hold that till the end, if there's time, that makes sense. There's a less broad one that just came in that says, what's a real gain from hyper-threading on multiple core machines compared to the 20-40% of one CPU you estimated?
It's the same thing. So if you turn on hyper-threading, you get you double the number of cores, but you're only getting 20 to 40% more performance. That's what it is. If you have 1 CPU or 32 CPUs, it's the same thing. Yeah. You're not getting twice as many cycles to execute. You're only getting about 20 to 40% more throughput on the CPUs. You're reducing your latency by about 30 to 40%, but you're increasing your throughput by 20 to 40%. So if you are on a data warehouse, turning on hyper-threading makes total sense. If you're on an OLTP system, hyper-threading will slow you down.
Makes sense. So we've had another one come in. They said you can wait till the end. So I think back to you.
Okay. So 4 CPUs, same picture as before, just without the squares around these CPUs. So this is now the same thing. When you have 4 CPUs, one thing starts, you can only have 1 link between each one of the CPUs. So if this CPU needs anything from that CPU over there, they can use that link. If it needs something from here, it will use this link. If it needs something down here, it will use this link. Yeah. So now you have 4 independent CPUs running stuff. And as long as each CPU stays to itself, it performs still good. If you start needing to access constant data from the other ones, it starts getting crappy. Yeah, and this is what most people see. When you go from 1 to 2 CPUs, it's not that bad. But if you go from 2 to 4, it's a big difference. First big difference is this is no longer 3 connections. This is just one. Yeah, so that throttles your throughput. Yeah, and yes, yeah. And I will talk about this later a little bit more when it comes to storage. Yeah, because that's even worse. And so that's the big difference here. Yeah. So with 4, you will, if you don't do anything to optimize your system and help it run better, which I will show after I go through all the up to 32 cores, CPUs, you will see massive degradation. And that's what the graph at the beginning showed. You again, we doubled the number of cores, but we're not doubling the performance. We're adding percentage-wise now. Yeah, we're adding 20, 30, 50% on top of what we already had. Yeah, we're not seeing 2x, 4x performance anymore. Yeah, this is we're adding a little bit. Thing is, where it will help you is when you need throughput. Yeah, and you can run it independently. Yeah, just imagine a data warehouse. You run all your customer stuff here. You run your product queries here. You run your regional queries here, and you run something else over here. And each one can run mostly independently, and sometimes have to exchange data. Yeah, this is an awesome setup. Yeah, if you have an OLTP where you're working on the same page as we saw in Klaus's example before, you're trying to insert into the same table, and the table is right now used over here, and then it needs to be here, and then it needs to be here, and then it has to move around all the time. Yeah, that's going to be horrible. Yeah, that's things. Yeah? So if you go to 4, you have to start doing things, and we got through this. I want to stick with just what the CPUs. The challenges first before we discuss how we can make it better. Yeah, 8 CPUs, and then I'll start super simplifying the whole thing because otherwise we'll run out of space on the screen. With 8 CPUs, we now start to not all CPUs are connected directly anymore. Yeah, and this is where it gets tricky. So if this CPU needs something from this one, it's still a pretty simple thing. But if it needs someone from this CPU, it would now have to go here, here, here. No, it's not that stupid. There's always a way to do it with one hop. So it would do this and then go here. Yeah? So one extra hop to get to the other CPU. Yeah? It will not do like something like this. It will never do that. But thing is, yeah. So with 8 CPUs, this becomes an even bigger challenge as before. If you have to transfer data between them, and this is why most people, before the session when we were talking, that people said we had a bigger machine and it just performed crappy. Yes, because if you don't do anything and you just run it like a one socket machine, it will perform crappy, and that's not the question. But if you do something to make it run better, you will get something. Yeah. Now you have 3 levels of memory latency. You have local, remote, and remote via one extra hop. And yes, the bandwidth between CPUs is down to 1/3 of a dual socket. And if you're unlucky, it's even down to 1/6, because you might have that these 2 CPUs want to exchange data, and this guy wants to exchange with this one, which means it has to run through, this one wants to exchange, let's get rid of this. This one wants to exchange too, and they have to run through the same pipe at the same time. Yeah? So then is when you're down to 1/6 each instead of 1/3 when you just talk to the next one, or if you're the only one talking to the other guy. Yeah? So if you're the only one doing this here, you're still down to 1/3. But if 2 of them need to go at the same time, then you're down to 1/6 of the bandwidth available. And this can become a problem. So we're skipping 16 CPUs because 16 CPUs are basically the exact same as 32. Everything above 8 is basically not supported out of the box. So the Intel CPU has no idea, or AMD stops after 2 CPUs and Intel stops after 8. They have no idea how to connect to more. And some CPUs in the Intel space also stop after 2, and some stop at 4. Yeah. So not every CPU is thing is, but your hardware vendor knows which one. So 32 CPUs. This is how it looks like. I don't know if you can even see it through the internet, but that's how these are configured. It starts very simple. This is basically the same thing as this. Yeah, but instead of being connected with 4 connections to the other side, if you look at this guy, I remove all the stuff here. If you look at this guy has 1, 2, 3, 4 connections to the other guy. And it doesn't matter from which corner you look at it, it's always 4 CPUs are connected in a square, and then they are connected with 4 connections to the other square. If you look at the 32 one, that's the exact same thing. You have the square where each one is connected to the other one, and then you have 1, 2, 3, and 4 into that full mesh that is implemented by hardware made by the vendor. Yeah? And yes, I'm not naming the vendor, but you might figure out who it is. Thing is, yeah? So this is fun. And the interesting part is it's not much worse than 8 CPUs. And I say that lightly. Yeah. Within the 4 CPU node, it's the same as an 8 socket. It behaves exactly the same. If you stay within these 4 CPUs, you have the same behavior as with an 8 socket. It's a 1 or 2 hop connection and behaves exactly the same. If it needs to talk to another node, each one of the 4 CPUs has a direct connection to that ASIC, and that ASIC has a direct connection to any other 4 CPU node. Yeah. And here again, it's one thing. Yeah. So that ASIC basically is one more hop. That ASIC is one more hop than the thing is because it does nothing else. So it has much less overhead in it, and that's what a job does. Yeah. So from it's slightly higher latency with that ASIC overhead, which is, again, a little bit faster than if it would go CPU to CPU. And it has about the same throughput between the CPUs. So that's a good thing. So if you go above 8, it doesn't get worse. It's a big jump between 2 and 4. It's another big jump between 4 and 8, but then it levels out because they're putting a lot of extra hardware in to compensate for the problem. Yeah. And it's very clear, the more sockets you use, the more you have to actively support Pneuma. So, questions for 4 and 8 and 32 sockets especially.
Yes. So if we were in person and there was a microphone, you would have a line. So just tell me when to stop and we can kick all those to Slack or something like that. I've got a handful here. So I'll start with Hugo's. Sometimes there are multiple paths between CPUs with the same number of paths. Will it use a single pre-configured path or will it dynamically load balance between the paths?
So if you have a 2-socket machine, you have, depending on which vendor you use, you have 1, 2, or 3 connections between the 2 CPUs. They will load balance across them. Yeah.
Okay.
Yep. If you have more than 2 CPUs, it's always 1 connection or less.
Okay. And we just got another one, so the line is increasing. So once we hit a point where there's latency internal to the CPU, that latency doesn't manifest itself as high CPU, correct?
So latency within the CPU, you mean when it has to communicate with the cache of another core or something like this? It will kind of show up as high CPU because a command just runs. What all these CPU busy things show you is what they all do is they run an additional thread that only gets cycles if no other threads needs them. So when you hit 100, it means everything's busy all the time. Yeah, and you're getting nothing else. Yeah, so measuring CPU utilization is kind of a reverse thing. You are basically measuring, is the CPU bored and I can do more on it. Yeah. I can run a CPU at 100% all the time and your SQL Server will not be slower if I run the utility that pushes it to 100, one priority level below SQL Server, because it will never get a cycle. But if SQL is not using it, it will immediately pick up. Yeah. So 100% CPU utilization is an indicator something's wrong, but it doesn't really show you things. Yeah. And high latency inside the CPU will definitely show up as more CPU utilization.
Okay, we'll try to squeeze in like 1.5 more here. So Hugo said, had a quick follow-up, said his question was actually about the 8 CPU setup, where some the CPUs are connected through 2 paths of length 2. So I don't know if that changes the answer or not, but he wanted to get that in.
In an 8 socket, I've never seen having 2 CPUs with 2 links. No.
Okay. And we'll throw one more in here, and then we'll see for the next break. So somebody asked, what about the Azure 64 and 128 cores that we use for SQL servers? I assume VMs here. How are these configured?
They are pretty much the same as here. They just screw up the I/O part. From a CPU's perspective, they are awesome machines. They just, and we'll talk about it when I come to the scaling the I/O part. They are really bad in doing this.
Gotcha. Okay, yeah, we definitely have some more queued up, but I'm sure you've got slides you want to get to, so we'll shift back to you.
4 and 8 CPU and 32 core machines. They're just for high concurrency OLTP and high throughput. Don't use them for generic servers. Don't try to use them for low latency. It's a waste of money. Yeah. If you don't buy a big machine and then virtualize it. Yeah. That's a crime. Yeah. It should be if it's not. Yeah. I guess. Yeah. Small boxes for generic workloads. These big boxes, they have a very specific one. Yeah. I've seen people trying, can we buy one big machine and then put 100 databases on it? Like, yeah, yes, you can, but you can just give me the money and you stay with your current solution and we're fine. Because you will be worse off. Yeah. This is, if you have one thing, if you can fully separate, if you have 2 databases, don't grow the machine. Try to separate them on 2 boxes. Yeah. This scale up is not the solution for everything. You can scale up, but it takes a lot of effort, and we will get there. So, Pneuma, a little bit of recap from the morning and looking from it from the other side. So you connect from the outside, from your application server through your database server through a network connection, which is then connected to a CPU and memory, and that grabs somehow to your data. This is the one CPU setup. It's very simple. Every connection comes in here, and every connection uses the same path to do something. Yeah? Most modern machines, if you have 2 or 4 or more sockets, you have the problem, lots of people, and this is where I said most cloud providers mess it up. They still have one network card, which is still connected to one of the CPUs. So if that CPU should run something, that query comes in this way. Yeah, or to be more accurate, it comes in this way. Yeah, but it has to go through the first CPU. Yeah? And for example, if you do that, it might still be fine. But then you run something with maxed 4 that uses all 4 CPUs, and suddenly you have these CX wait packets. Why? Because the first CPU is much slower in running their 1/4 of the workload. Why? Because it constantly has to deal with the network card. Yeah. And this is where you then see unbalanced workloads, CX packets. I love them. They're not evil. They're just telling you you are keeping one CPU outside of SQL Server more busy than it should be. Yeah, because if all 4 would run at the same pace and would have enough, the same amount of time for your query, they would finish all 4 at the same time. Yeah. So removing that bad query way of doing things. If you put in multiple network cards, and my recommendation is 1 network card per CPU. Doesn't matter how many CPUs you have, 1 network card per CPU. Yes, if you have 32, it's a lot. And I remember the times in the past where I had a machine with 128 CPUs. Each one only had 2 cores, but still was a lot. We had 128 network cards, and they were all connected at the same time. And queries were spread across them. So the way you embrace Pneuma is by you partition your data between the Pneuma nodes. So you're basically, a simple partitioning key would now be CPU modular number of CPU. So that gives you 0, 1, 2, 3, 4, 5, 6, and 7. Yeah. And on your application, you do the same thing. You know that a record is in partition number 4 because it's custom ID modulo 8, which translates to number 4 in this example. You know your record is here. What your application server does is it calculates, hey, custom ID modulo 8, that's 4 in our example, and I go to this network card, yeah, which is just, you have 8 connections open to the same SQL Server, each one to the other network card that has an independent name, independent IP address, and you come in with the query here. And the next query that deals with the next customer, where the modular calculates out to 6, comes in here. And I think I just threw a lot of stuff that I already have with nice arrows. Yeah, same thing here or here. Yeah, so each one of them, you teach your application, hey, this is a very big box, and we have to talk to it through 8 different doors. Yeah, it's the same thing you would do with human beings. Yeah, you know, you have 8 different departments that do something. You can push all the work to the first department, and they hand it off to all the other departments, or you pre-sort your stuff and you throw it to the right department immediately and go there. Yeah. So, can it be perfect? No. Will there be mistakes? And sometimes this guy needs some data from over here. Yes. The emphasis is on sometimes it doesn't matter. Yeah. If it's every freaking time, it's bad. Yeah. If you do the math wrong, and every time you come in here, you need something over there. Yeah. You come in here, you need every time because you have your modulo wrong. You use a different algorithm here than you use here. Yeah, you're screwed. But it's helping it a little bit. Yeah. And you will always have tables that you cannot partition. In this, my example here, I partitioned the customer table because we have much more operations that are per customer. The same good would go by orders. Each order is assigned to a customer, so you would partition the orders in the same fashion. But if you look at your products, your items, that would be one table that is randomly distributed between all 4. And every time SQL Server needs to join with items, yes, it has to go cross. Again, it's not like you can't do it at all. The idea is to reduce it as much as possible as you can. Yeah? And just choose one partitioning key, help it out against the odd. Yeah? So this is Pneuma. Soft Pneuma allows you to go one step further. We remember we had the one network card, one CPU, one thing is, but this CPU has multiple cores. So what we can do is, for each core, we can create a soft Pneuma unit and assign it with a different IP address or port number to that individual core, and then just access that. So our example before, we did customer ID modulo 8. But let's say we have 8 CPUs with 8 cores each to keep the math simple. That would be 64 individual partitions. We partition the table into 64 partitions and modulo it by 64 when we spread the load. Yeah. The reason for that is that you even further help your CPU by having the chance that the data is in the local cache for that CPU, increase the chances for that. It's still going to be the same memory on the same chip here. Yeah. But the chances, if the same customer comes in the same core all the time, that the data that they need is already there. In a sales application where the typical customer does 1 transaction per day or 1 per week, that doesn't help you. This is for the case where you have this Internet of Things out there. It's that little measurement device that sends you a temperature read every 5 seconds. Yeah. If you push it into the right corner of your big server, there's a big chance that that record is still in the cache from 5 seconds before. Yeah. And if not, it's at least on the same Pneuma node. Yeah. So this is where you have to think. Should you do this for your garden variety application where you do a couple of transactions per hour? No. This is for example, doing that spread out. Coming back to Klaus's example before, he tried to insert a couple of 100,000 rows in a second. doing this, you can push it to insert like 1.5 million rows per second, as an example. Yeah. But you have to do something, because what you're doing is you're basically making each node work independently from the other one, and therefore you push up your scalability by a lot. So I have to talk about ledges as well. There's something that very few people see in their lifetime. It's called super and sub ledges. Imagine, and I will draw this here, you will encounter them on systems with many Pneuma nodes and many cores. Yeah? And what they basically do is they duplicate active pages that are mostly read-only, like index root pages, to every Pneuma node. So when we go and we have our individual Pneuma nodes with the memory in it, instead of having a page once and each one has to go here to read the same index root page, what they do is they say, hey, we create a super ledge, and then we make a copy of that page on each node, and we're fine. If you need to read that page, all you need is a ledge on your local page, on your local CPU, local memory, and you're good to go. If you want to write that page, if you want to modify it, what you have to do is you have to acquire the super ledge, which basically goes down and acquires a ledge on each and every node. And then when you write the page, you have to write it each and everywhere to copy. Yeah. So don't do this on your leaf pages, and SQL is very clever. So the only thing that SQL Server considers there is basically index root pages and only stable ones. So it would not, on a small table, if they basically look, is this table modified a lot, then this page modified a lot, then we're not doing it. But if this page sits there for hours and hours with no content change, then this will speed it up a lot. Yeah? They introduced that, by the way, in SQL Server 2008, when they first ran on the Superdomes with 64 cores, and it boosted the performance immensely. Yeah. So SQL does stuff internally to do this. Yeah. So for all reads, you need a ledge on the local copy. For writes, you need a ledge on each one of them, and then do the write n times. Yeah. And again, it's an internal feature. But don't be surprised when you see new ledge types that you've never seen before, because they don't exist on a small box. They never exist on a system with 2 nodes. I've never seen them there. I've started seeing them 4, 8, 16 Pneuma nodes. That's where they start making sense. I don't think they make any sense on a 1 or 2 socket machine. 4 and up, they might be around. Good. When should you actively support Pneuma nodes? Low latency, yes. If you want the lowest latency, direct your query exactly where your data is. High concurrency, of course, you don't want to influence any other thing here. Yeah, that's it. So, questions?
Yes, there are a multitude. So I'm going to handle one that came out of the Slack channel, because we don't have a good way to record those like we do in here. And that was, how do you assign the NICs to the individual CPUs, and how do you configure that?
Okay, so there's a tool around. If you Google Pneuma config tool, it's a little thing that it's registry keys. Microsoft never made it like nice. It's purely hex editing in the registry. Yeah. Someone wrote the tool that is there. I wrote some PowerShell that does it for my setups. It's basically ones and zeros in registry keys that assign them. So it's basically you take the IP address and you say it. Yeah. The easiest thing is, and if you look at the latest version of SQL servers, like 2016 and up or 2014 and up, they start using soft Pneuma by default by breaking larger CPUs into smaller bricks for the same reason. And they just create the registry entries for you. But there's a tool, there's a GUI where you literally click, I want this IP address mapped here, I want this. And inside SQL Server Configuration Manager, and it's a very bad idea. No, I'm not doing it. Can I?
So while you're going through that, kind of the overarching question we have is, There are 9 outstanding questions in the Q&A panel. Obviously, only 15 minutes left. I'll hand you over to Anthony or Rob, I think, here in a minute, because I have a breaking issue that I have to handle. What would you like people to do? So there are records of this. Do you want the organizers to email you questions? Do you want to tackle them in Slack?
At the last slide, I have my email address, and everybody can email me questions after that. I will try to answer as quickly as possible. But if it's hundreds, then it will take a day or two. And yeah, all the questions that are here, if I get them, I will answer them in like a little document, a text file, and post it right next to the slides.
Okay, awesome. Yeah, there are several. Like I said, there are 9, and as you might guess, they're a bit detailed, some of them as well.
So let's use the 15 minutes to go to the slide deck, and then I'll stay around for questions as long as till they shut down the session. Yeah. So CPU affinity. It's the next thing. If you have a core and you add a schedule, each core has a scheduler on top. That's a one-to-one relationship that never changes. While you run SQL Server, it assigns one scheduler. On the other hand, the query gets assigned to a worker thread. There's many worker threads, way more worker threads than other schedulers. And then SQL Server assigns the worker thread to a scheduler and runs it. Yeah. After a while, when it gets off the scheduler because someone else has run, the next time SQL Server might assign it to a different scheduler. This is when the CPU is not affinitized. This is the normal behavior. The best way to show that is you have a bigger machine with a couple of cores, and you run an index rebuild and you run other queries in parallel. While the index rebuild is running and you look at your CPU, one is at 100% because it's doing the index rebuild, and over time it will move from CPU to CPU. It's really funny to watch because every time the scheduler picks a different one, it's rarely coming back. Yeah? So that's that. And then it goes back to the original scheduler again. Yeah. So what happens, you can affinitize, and you can do it through the GUI, or usually when you have bigger machines, you don't want to click 100 or 1,000 times. You want to do it through T-SQL, where you can say affinitize auto is basically, we don't have any affinity set at all, or you can affinitize certain CPUs. That gives you 2 tools. A, it limits the CPUs this instance is running on. So for example, if you have 2 instances on the same box, you can give 8 cores to one instance and 8 cores to the other one. By the way, that's the fastest way to virtualize on SQL Server. It's the fastest way. It's faster than running 2 databases on one instance. It's way faster than using any kind of hypervisor. And you can assign a whole Pneuma node and affinitize a whole Pneuma node. Yeah. If you have auto, the query while it's running can migrate between all the schedulers and cores. If you set an affinity, the scheduler can only pick the worker thread will only be running on one of the selected cores, and it will stay there, and it will never move. And then you can set the trace flag 8002. That means you are selecting a certain number of cores / schedulers to only use these, but the query, as with auto, can migrate between them. Yeah? And that is important because while on an OLTP system, you want to set maxstop to 1. You never want them to go parallel to begin with, and you want to have them stick on the same schedule and not move around. Yeah, but in a data warehouse, you don't. In a data warehouse, you want them to be able to migrate between the schedulers because it might be that much more data is on that other core, and you want SQL Server give the ability to move there. So going back to our slide, in low latency, you want to affinitize again. High concurrency, you want to affinitize. For high throughput, you might not want to affinitize unless, and that's in the next couple of slides. Generic servers don't affinitize. It's just too confusing. So scaling I/O as well, and I have to speed up a little bit to go through all that content. The wrong approach is you have your box, which is 1x in size, which is your baseline, which has 1x CPU memory and everything. What I see most people do, the average is 1x size. What I see is we want to have an 8-time bigger machine. So we give it 8 times the capacity. But we give it 8 times the CPUs, but yeah, memory is expensive, so we only give it 4 times the memory. We use the same network card because the switch won't change anyway. And yeah, if we are really lucky, you get like more connections to your storage array. Yeah, and the latency to the storage array will definitely stay the same. Yeah, and that's not what you want. That's half the speed in the best case scenario. Usually it's even less. Yeah, so that's the wrong approach. This is how people do it for 50 years, and it's so hard when you start in a company to explain to them that's not how you can scale. This will never work. And this is why so many people, they buy a bigger box, say it's crap. Yes, because you did not scale any of the other ones. You only scaled the CPU and your capacity, and that's not how it works. Yeah, so let's throw that away. I'm gonna skip over that. Current storage options, very quick. SAN should not be on the list. If they want to connect, if you talk about scaling beyond anything that has 2 sockets, even with 2 sockets, I wouldn't use it anymore. But anything above that, SAN is your bottleneck, and you will die trying to use it. Yeah. Just to explain, SANs still measure latency in milliseconds. Yeah. Even if they use flash. Yeah. They might get to 0.2 milliseconds, but that's not what you do. Is microseconds and nanoseconds. That's how storage latency should be measured these days. With NVMe PCI Express cards, you can do a petabyte in 70 minutes. Yeah, the same thing on a SAN array will take you a day and a half. Yeah, you can with persistent memory, you can do 24 terabytes in about 300 seconds. Yeah, with NVDIMMs, even more, you can do 1.5 terabytes in about 3 seconds. And the reason I didn't list a petabyte here is very simple, because there's a limit how much you can connect. Yeah. So this is current options. For a low latency server, we have our one CPU that we have. We have all the memory modules, and we fill the box up with as much memory as we can, because whatever is in memory is for sure faster than if it's on storage. And then we put in as much storage as we can and we need. And this is NVMe drives that are directly attached. And then we put a network card in the remaining PCI slot. So that's what you have. And that's the basic building blocks. Yeah. So this gives you about 60 terabytes, up to 60 terabytes. If you take smaller drives, you get less. Yeah. 60 terabytes. That's 1.5 terabytes of memory. And that could be 2 times 25 gigabit Ethernet. Yeah. And just to be very clear, that's less than 30K to purchase, including the storage. Yeah. So you didn't hear it from me, but that's the price of that box, including the memory. Sorry, it's not 1.5 terabyte. It's 768 gigabytes, one CPU. You can do the 1.5, but then it's not 30K. You need the newest chips, and they are insanely expensive. If you take out one of the memory chips and you put in one of these NVDIMMs, which is basically a memory chip with a battery glued to it, you can do about 1.5 million inserts, as Klaus showed you before, per second on this box, from multiple threads through that lowest latency on inserts possible things. The commodity server, the one with 2 CPUs, is basically the same box with the difference. It's higher latency, twice the memory, twice the disk capacity, twice the CPU. You can go up to 128 cores, 112 cores on Intel, 56 cores if you don't want that tricky core thing. It's the exact same design. The important thing is you have to scale it. So you see, now I have 2 network cards, one on each CPU. I have twice the number of drives. I have twice the number of memory chips. Yeah? Very important, balancing. Yeah? I remember this morning a question that was, we've seen a server, but we only see memory on 2 nodes and we don't see memory on the other 2 Pneuma nodes. Yep, they didn't have that configuration where, and this is so common. This is so common from hardware vendors. They give you 2 CPUs, they fill them in memory, but they put all the IO on one of the CPUs because they save you the money of like $25 to give you a second PCI razor in your hardware. Yeah, this saves you $25, and you just gave away half the IO performance, and Pneuma will suck. So don't do that. And this is the worst one, and this is the one I'm referring to this morning. They had 2 CPUs, or they had a case before, and only half of them were populated with memory. That means any memory access from that CPU has to go through the other one. That's insane. Go away. Yeah, don't do that. This is how it should look like. 1 CPU, half the stuff, the other CPU, half the stuff. Sometimes you can't do it and you have to like have 3 drives here and 4 drives here, something like this, because you're physically constrained. But then you should look for a different vendor because it's possible. And that goes back to the question, how do you find the hardware, the best hardware before? What you have to do is you have to test, or you find people like me that do this for a living. You shoot me an email, and I can give you pointers. I can't give them in public because that would be illegal and violate the license agreement that you have with your hardware vendor, because you can't talk about the performance in public. But I can have a nice little email chat with anybody and share my experience in a one-to-one session. So last thing I want to go through, IO Affinity. That's the second affinity you can set with SQL Server. What you have on a CPU, what you want if you have bigger systems, or the moment you have more than 1 CPU, IO Affinity might help you. On 2 CPUs, not much. On higher ones, yes. So first, what you should do is you should take 1 core out of the CPU affinity. So if you have 32 cores, define 1 for IO, the other 32 for things. This will not affect reading your data files. Your data files will still be done by each core individually. What this means is that the transaction log, the buffer, the memory buffer that is used for the transaction log, is affinitized to that 1 CPU. It will not move around. Yeah? And that means the IO process that grabs that data from that buffer will be running on that 1 core, on that 1 CPU that you affinitize it to. And that should be the CPU that has the NVDIMM. Yeah? Because then this is your log buffer in your memory here, and it's on the same CPU as here. If you have your second CPU and your log buffer is over here, and then every time you have to go through the other CPU to write it to that memory DIMM, that would be horrible. So let's get rid of that. Yeah? But if you have it on the same CPU, it's really great. Yeah? So doing that, and then you have your NVMe drives where you actually put the log files, and these drives should also be connected to a PCI bus that is on the same CPU. And then if you're really good and you torture the vendor a lot and they give you an extra registry setting that allows you to affinitize the driver to the same core that you affinitized SQL Server on. So we have SQL, the log buffer, onto 1 core. We have this on the same CPU. That means that core has probably a cache image of that. And then we have the driver that runs these IO things on the same core. Yeah? That means your log write goes into a cache, gets duplicated on the NVDIMM, but then when the NVDIMM gets copied to the drive, the data is already in the cache of the same core and can just be written down here. Yeah? So that massively things. Yeah. So this is how you get to 1.5 million log writes per second instead of 500-600 then you can do on a SAN. So to write that down, 500 versus 1.5 million log writes per second. SAN this. Yeah. As you have to do. That's log write. That only helps you with inserts. Yeah. And there's a setting inside SQL Server, persistent log buffer on. If you have that battery thing, you have to tell it that you have that battery. SQL doesn't figure it out by itself. Thing is, yeah. So you're setting your IO affinity when you have, again, for low latency, high concurrency, and for high throughput. But for high throughput, you also need to set that trace flag I mentioned before. And if you set IO affinity, you have to set CPU affinity as well, because it doesn't work without. You cannot affinitize a core that is used by SQL Server for the log buffer. So this one had CPU affinity already. This one, now you need to add CPU affinity if you're planning on doing the IO affinity as well. If you're just having a big data warehouse where the load and everything is not that critical, don't waste your energy on figuring out how to do that NVDIM and everything else. But if your data warehouse load has limits and doesn't finish anymore, that is a way to fix it on a large box. This, I'm just going to skip over it. I'm thinking is, yeah. One more important thing, if you have like this 8 CPU setup where not every CPU is connected directly, and you need to do a RAID between 2 drives, which is done in software RAID on these big boxes, which is much faster than a SAN. You can either hook up the 2 drives to the same CPU, or if for any reason you don't want them on the same CPU for redundancy reasons, because you might want to have the connector redundant, you can connect them. You should connect them to 2 CPUs that have a direct connection. So here and here, if you connect them to 2 CPUs that are not directly connected, your RAID software will suffer massively, because it constantly has to go through hops to synchronize the data. Yep, that's just a tip. Unfortunately, we're running out of time massively. That's the direct attached storage, how you can double the capacity by using PCI Express switches for your data. It also gets the thing up. Yeah. So, questions. Thank you for listening. I don't know who is still here.
So Thomas, firstly, truly super end last session. That's definitely done some mind melting. We have a few thousand questions.
Yep.
So as you know, Matt had to leave us. So I'm going to start with the one that
I'm going to regret this, but look here. So this is my email.
I'm going to start with the one that I can understand, which is, can you explain how max stop setting translates to Pneuma CPU cores hyperthreading?
So first of all, if it's high performance, there's only one max stop setting that you should use, max stop 1. Yeah, and let me explain that. Yeah, max stop tells max stop 1 on an instance level tells SQL Server, don't bother figuring out if this query should go parallel or not. Just don't run it parallel. Just run it as a single threaded. That doesn't mean you shouldn't run parallel queries, but you should not waste SQL Server's time to figure that out. You have a massive big query, put maxstop equals 64 if you have enough cores to do that, or maxstop equals 8 at the end of the query as a hint. That's one of the hints I'm agreeing, because you're saying this is a big query. I know it's going to take a lot of juice to run it, so I'm requesting more. And even if you have maxstop equals to 1, you can still run a maxstop equals 8 query if you put the hint in. Maxstop 1 is not limiting you. If you set maxstop to 1 on resource governor, that's a different story. But again, then you're not in the high performance business. So maxstop on the machine. The problem is your developer figures it out once. Yeah, that's a big query. We use multiple threads for it. It makes sense to run in parallel. Yeah. But why would you ask SQL Server to figure this out every time it runs a query? And especially in the mixed workload systems where you have thousands of small queries and then one large one. Yeah, because look at most OLTP systems. Yeah, they run both small and large queries, but the large queries are rare they don't happen often. Yeah, get the developer to put the maxstop 8 in, and the thing is, yeah, how much should you have maxstop? You should never have a maxstop larger than 1 Pneuma node, because then SQL Server can still run it within 1 Pneuma node. If you go above 1 Pneuma node, you will have funny effects. Yeah, that goes for queries. If you do an index rebuild, go maxstop whatever your system allows you to do. Yeah, because you want that out of the way as quickly as possible. You don't want your system be hold up things, because you're probably blocking and locking everything anyway. So let's get it done as quickly as possible. But for normal queries, I would not recommend going above a single Pneuma node. If you only have 1 Pneuma node, I would not go above half the number of cores, because the problem with parallel queries is they only work to your advantage if each portion of the query can be done independently in about the same amount of time as the other portions. And if this is not possible, so if you already have a query that pegs 1 CPU to 100%, and then you run a query with maxstop of all your cores, that 1 core will not get any work done. But SQL Server will schedule the same amount of work for that 1 core, and then you see these hours and hours of CX packets, meaning the other cores are waiting for this one to finish, which they're not actually wasting time. They're just telling you, yeah, we're waiting for this guy. We're doing other stuff. Yeah? But it's the problem. Yeah? And I get it that maxstop makes lots of queries faster when you run them in parallel, but in the high-end business, you specify it on a per query basis. That is much more efficient than doing it in a general way. On your garden variety general server, yes, pick a number that is not too high and not too low. In most machines that I work with, it's somewhere between 4 and 12, maybe 16. And we're talking about boxes that usually have between 2 and 3 times as many cores as that maxstop value is.
So we've learned something from the session, and we've learned that 2 CPUs is better than 1. So Anthony's going to ask the next question.
Yeah.
So, oh, okay. So, now that was the joke. I missed the joke. I was like, wait, there's no question in this list about 2 CPUs. All right. So generally, there's a couple patterns in the questions to cover. Do you want to offer any? You can pick which one you want to go after. Do you want to offer any guidance about how to apply these techniques to virtualization? Because we're talking a lot of questions around how you use scale out or up in virtualization. And the other kind of main theme in the questions, Thomas, is can you describe how you have applications connect to those multiple NICs when you had that distributed network card scenario down into the separate memory controllers and processors? If you want to grab either one of those, go for it.
Yeah, so I do both. So first one is the virtualization. In a dream perfect world, if I would have to build virtualization from scratch, I would take a box with one CPU with as many cores as that CPU can run, put all the memory I can squeeze in on that box, and then since it's virtualization, I have to deal with SAN, because otherwise you can do all the vMotion magic and everything. Put as many storage controllers in that box as I can, yeah? And then put a hypervisor on top of it, and then you can define VMs in any size, and you will have no issues. Yeah, because you have 1 CPU, and you split it between whatever you virtualize on there. Yeah, then that's a no-brain configuration, and this will give you the most juice out of the box. I get it that for density reasons, lots of corporations want to add a second CPU here. Yeah. The problem is, if you have that scenario, you have 2 options. You have an option that you take a VM. If you have then 2 VMs, that you run the one VM on this CPU and the other VM on the other CPU. Yeah. CPU. That's one option, and that might be great. And you're certainly getting it. The other option is that you take that away, and you take half the cores from this CPU and half the cores from the other one, and run both VMs here. And people like Alan Hurt and David Klee have written hundreds and hundreds of pages of white papers that explain why you should do either one or not do either one of them. Yeah, it's if you're in a virtual world and you see constantly performance issues, try thinking about maybe virtualization is not the right thing for that workload. I get it. Some places want you to do virtualization because they want to do everything the same way. But then think, if you constantly still have performance problems, use one. When you do virtualization, when you create the virtual machine, it's very clear. You have to tell the VM the setup. Yeah. So in the first setup where we had a one-to-one mapping, you would say it's one Pneuma node, it's one CPU in the virtual machine. In the other one, you would tell it it's two CPUs and two Pneuma nodes. Yeah. So you create it that way. Yeah. You can still have just one CPU and create two Pneuma nodes virtually. That will still work as a better. The second problem is if you run multiple CPUs on the hypervisor, and the bigger the VM gets, the harder it gets for the hypervisor to give you all the cores. The problem is if you are on a VM with 16 cores, they can't give you 15 because they don't have more right now. They need to give you all 16 while you're running, and that's a big problem sometimes. I personally try. So in production, what I advise all my customers is don't oversubscribe CPUs to begin with. That means I do the same thing as Microsoft does in the cloud and AWS does. 1 or 2 cores are reserved for the hypervisor. They do not get assigned to VMs. And if then, for example, I had 64 cores to begin with on the box, I assign up to 62 cores to the VMs. And the total number of cores in the VM cannot exceed 62. Yeah, that's just for production because I don't want to deal with oversubscribed CPUs to begin with. Development environment, totally different story. Yeah, 200 VMs on one box with 10 cores, we're good. Yeah, write better code, it run faster. It's training, but yeah, it's
if it runs well there, it'll run well in production.
Oh, yeah. Thing is, yeah. If you need to go above, I usually don't see much gain to go from 8 to 16 or so, because then the problem of not getting all the cores and waiting for it just runs pretty high the risk. So the other question was, what was the second one?
Basically, how do you get applications to connect to any one of those independent NICs to guarantee that
this
you're
is
hitting
really
a
hard to
specific
show on a
number?
workstation, but I try. I try, and this is don't do demos without doing this. Where is this freaking thing? Now you see all the secret tools I'm using. No, it's on the server. It's this nice little thing. I think it's computer management. I hope it's there. Hello. Yes. So, and you probably can't even see that in my screen share, but if you go there, SQL Server Configuration Manager, and I hope you see I have way too many instances installed. Yes, but that's not a running one. Yeah, but it shouldn't matter. So if you go in SQL Configuration Manager, and in the network part, the TCP/IP protocol, you see these IP addresses over here? You can create new ones in the registry, and when you create them in the registry, you can add more IP addresses. My tip is, if you don't want to deal with the registry, add all the IP addresses to your network card before you install SQL Server, because then SQL is really nice and creates all the entries for you. If you forgot that, you will be sitting in the registry and typing hex numbers for a long time. But once you have that, you can do and say, for example, this one, IP7, which is, let's take a TCP/IP. So this one, IP4 port. And what you can now do is, so this would go to Pneuma node 4. If you do the angle brackets and the 4 here.
What?
Yes. So everything coming in, it's Microsoft. It was a quick hack. So this is everything to that IP address goes here. But then you can do, oh, I want port 1500 goes to 4. Port 1600 goes to 5, and so on. Yeah. So, yes. And again,
all I can do is laugh.
Right.
It's painful. The nice thing is you can do all that from PowerShell.
Okay.
The problem is PowerShell is not designed to do that, because all PowerShell do is call read registry and write registry, because this is all registry entries. Yeah. So I have to talk with the company I wrote this for if I can share it. If you're interested in actually doing this, give me a call. It's about 600-700 lines of PowerShell where you have a nice little config table in a SQL Server that says this IP address goes here, there, and then this PowerShell reads that configuration nicely from the table, connects to that machine, and does all the matching in the registry, and then reboots the box, and it comes up again and works or not. So far, it worked all the time, but it adds all the nodes, it removes it. It's tedious, but it's not rocket science. It's 5 or 6 registry values per Pneuma node, and that's it. Yeah. But anyways, yeah. So yeah, that's basically how you do that. Sorry for the small font, but I have a large monitor. So and thing is, but so to show this a little bit better, let's use the newest documentation tool. So for everybody. So it was basically, if you do this, it would connect to Pneuma node 4. This would take port 1433 to 4, and then 1435 to Pneuma node number 6, and so on. Yeah? And how small you make your Pneuma nodes. Normally on a 2-socket machine, you have 2 Pneuma nodes. But if you add soft Pneuma, you might have 16, 32, whatever Pneuma nodes. I would not go above 64. And that is just experience that lots of tools and Microsoft development code has issues when you go over 64 Pneuma nodes. So don't break 1,000 server, 1,000 core CPU into 1,000 Pneuma nodes.
So we only have about 3,000 more questions, but Andrew's
Yeah.
on top of 9:30 on.
We are at the end of the event now. We have 1,000 more questions for you, but as the old saying goes, leave them wanting more.
Right. And we will get the questions to you.
We will get the
Thomas.
questions to all the speakers. I'm just going to grab the screen here.
Yeah, I will upload the slides in the next 5-6 minutes to the Git thingy.
Fantastic. Yeah. So we have. Please